There were 600 people. Thank you. We have to sort this out, the connectivity issue, but we'll do that. Thanks. Dipanjan, is my sound okay?
Yes, Somak, the sound is fine.
Yeah, just changed over. Okay.
Somak, just before you begin, so should I ask one of the PhD students to be in the lecture and help you? I think there's already Prakash.
That's fine. I don't think that I need that. That's all right.
Okay.
Share screen. And there's people still coming into the waiting room.
Yes, since there's a huge number of participants, it takes some time for the waiting room to.
Let's wait.
But it's almost done, so you may start.
Okay. Okay, I'm starting now. Okay. Thanks very much. It looks like a lot of people here. Good morning and welcome. I'm very sorry that we had this delay. And the first day we are having some technical difficulties. Let's see. Right. So what I'm going to, you already had a lecture in the and so people have explained to you how this is going to go. I'm going to in the next today and in the next 3 days talk about a basic introduction to astronomy, astrophysics, and I'm going to assume that people here have not done any astronomy before. And that's true of a lot of people, but it's also not true of many people. So a lot of you will have done quite a bit of astronomy in school, in various other courses that you might have taken. So if you find that I'm saying things that you know already, please bear with me, because as I said, there is a wide variation amongst the people who are attending this course in terms of their expertise. Also, I'm aware that I have a large fraction of people who are university teachers and teachers of physics, and so their level of knowledge in the subject is very different from the other part of the audience, which is the undergraduates and the graduate students. So you have a big spread of people attending. So I have to keep that in mind. So please. So today, as part of this introduction, I'm going to talk about naked eye astronomy. So this is mostly talking about astronomy as you would do if you didn't have a telescope, and the basic idea of the scale of the universe, and also the what you see in the sky and how to look at it. And since I started a little late, I'll go on a little later than advertised, and so I'll go a little past 12:30, and then I can take a couple of questions, but it's very difficult with 700 people or 600 people to do a lot of questions, but we will see how to do this. Okay, so this is the beginning of this introductory bit. Now, as you probably know, I mean, you in the morning you had the introductory lecture, but you know that I belong to Ayuka, and Ayuka is the place that you would normally come to if you were doing this in person. But Ayuka is essentially an institution that has been in Pune since 1988, so we are more than 30 years old. It was set up by Professor Jayant Narlikar, who's very famous astronomer, scientist in the country, and he still very much comes to his office and attends. Even during the pandemic, we have seen him around. And our job is, and this is why we have this spread of people attending this course, students and teachers. Our job in the country is to essentially bring together universities. We are the inter-university center, so we are the link between universities. And the idea is that it was set up in the 80s when there were very few places in the country teaching astronomy and astrophysics. And all over the world, astrophysics is very much a part of physics department, or often there are departments of astronomy that are separate, and all physics programs have astrophysics as a part of their course. But certainly in the 80s, only 5 or 6 universities in India would teach physics as astrophysics part of physics. There are some places that taught astronomy as part of mathematics. It's a very different kind of astronomy. And the idea was that Ayuka will help set up astrophysics teaching and learning across the 700-800 universities in India, or whichever the universities teach physics. And it has evolved quite a lot, and now close to 100 universities teach physics. Astrophysics is part of not just physics, but we have astrophysics in departments of engineering. We have departments of statistics and biology, and mathematics and physics teach various versions of astronomy, and that is growing. And in the new education policy, because the teaching of subjects is modular, then you will find that more and more small, short courses of astronomy will get into various subjects. And we are looking at interfaces between astronomy and biology, astronomy and statistics, astronomy and mathematics. Teaching astrostatistics courses here in Pune University. Astrobiology is being taught, astrochemistry is being taught, things like that. So this is how astronomy education comes into it. And this all started with when Ayuka was set up. And we now have this teaching learning center in Ayuka, which is funded by partly by the Department of Education, where we actually develop courses for university teachers. And so the refresher course is not just the only way where university teachers who are not trained in astronomy can get astronomy education. And so in the larger scheme of things, please let us know if you are interested in learning more about how to teach astronomy and also what to learn in astronomy. Right? So we are, by the Government of India, the designated resource center for astronomy astrophysics. And we have associates now, about 179, 80 associates from all over India. And you can see that the spread is a lot. I mean, actually, this has not been updated. Now we have an associate in Tamil Nadu, but there are quite a few in all over the country. Okay, so having said that, now let me just start on astrophysics and astronomy. I mean, a lot of people ask this question: why do we study astronomy and astrophysics? Other than the fact that it helps us understand. I mean, this is a famous woodcut from the 18th century from Jean Flammarion, where essentially talks about a medieval explorer going out into the world, and at some point being able to pull aside the curtain that divides us, the Earth, from the universe, and have a peek into the universe. It's kind of an old idea of the heavens, the sky, and whatever is in it is away from the Earth. It's different from the Earth. And in almost all traditional views of the universe, of course, we actually learn more from the tradition that comes from Europe, through from the Greeks and the Romans and things like that, because that's the thread of science that we learn. The heavens were considered to be completely different from the Earth and made up of a different element called the fifth element, the Earth being made up of four elements, everything that we experience. And so the heavens were supposed to be away from Earth. And starting from Galileo, we started changing that. Galileo showed that the moon is made exactly the same as the Earth. There are satellites that go around Jupiter, so according to popular belief, everything goes around the Earth is not right, and things like that. And the view changed. And now it's so different that we are at the other end of the spectrum, where we can assume that the laws of physics that hold here on Earth actually apply everywhere in the universe. And we go and apply it everywhere, and we haven't come across many places where they don't work. And there are many cases where, some cases where it seems that they don't work, and then we want to see how we can understand this better by looking at within our physics framework or within our scientific framework, how we can understand this. So the heavens is not separate from the Earth. And only in the last 100 years, you would find, as we go along here, you will see that only in the last 100 years have we started figuring out how large the universe is and where the Earth is and the sun is in this whole scheme of things. So this is a very new thing that we've learned, very new thing that we are learning. Astrophysics is a very, very new subject, right? So, but it's also the oldest science. That's the paradox. And it's the oldest science because people have been looking up at the sky from whenever they started to wonder about things. And they try to make an idea, they bring up ideas about how the universe worked. It's not necessary that they were correct, but they started investigating what the skies are much longer than any other science. And so it's the oldest science, but it's very new. Astronomy is the oldest science. Astrophysics is a very new science. And this whole question of why study astronomy and astrophysics comes also because people think that our job in astronomy and astrophysics is to actually go and look at the universe and study the universe. So it's something exotic, right? But it's not. Because astronomers and astronomy and astrophysics, when you do that, it's such an interdisciplinary subject. It brings together many, many branches of learning together to study the universe. Remember, we are working with things that we can never touch or go to. If you are a solid-state physicist, you come into the lab, you have a sample that you can prepare, and you put it under a microscope and things like that. You're a biologist, you can actually handle your objects. You're a chemist, you can mix chemicals. And you can repeat an experiment. In astronomy and astrophysics, we can't repeat the experiment. The universe is an experiment that's been given to us. And we can't also go and visit a lab where we can perform the experiment. We just have some very imperfect information, partial information that comes to us through various kinds of radiation. And from that, we have to make sense. So the astronomer's job is like a detective who's appeared at the scene of murder days after the murder has happened. Nothing is there, faded clues everywhere, and we're trying to figure out what happened, right? And that requires stretching subjects to their limit. And that's why we need engineers, we need all kinds of engineers, we need computer scientists, we need physicists, we need chemists, we need mathematicians, and now we need biologists to put together a lot of this information. And out of this, because we are stretching the technology, out of this comes a lot of things that you don't think astronomers have given you. For example, astronomers have given you the digital camera. the thing that's in everybody's pocket now in their phone came because people realized that they can't send out the Hubble Space Telescope to space and bring back films and have them developed to make photographs. You need digital photographs. And that's why the CCD was developed and the digital camera was developed. The GPS system comes out of basic things that astronomy uses. The CAT scans and whatever MRI that you do in hospitals was developed by an astronomer. And things like that. There are lots and lots of things that I can point out. In fact, the entire scientific inquiry comes from an astronomical question where Halley went and asked Newton, why does this comet come back every 75 years? Right. So it was an astronomical question that started Newton thinking about physics. So astronomy has a huge application. I'd like everybody who's on here to switch off their cameras and also their sound for the time being, and because there seems to be a lot of people, right? And that does interfere with the bandwidth. Right. Okay. Fine. So now, having motivated why I'm doing astronomy, let's look at like the basics that we're going to do. As I said, we're going to work with this today. I'm going to talk about naked eye astronomy. Just to orient yourself in the sky, and what would you do if you look at the sky. But just before that, I just wanted to talk about the scale of the universe, because the numbers are so big in astronomy that people have a very much of a difficulty in getting their heads together in terms of very large numbers, in terms of distance, in terms of time, in terms of scale, mass, etc. So here we are. We, just because the numbers are so big, we would use the basic unit of distance to be one parsec. You will hear this many times in this whole course. A parsec is about 3¼ light years, about 10 to the 18 meters, and that's, we use that, and I'll motivate that later on why you use that, but it's essentially related to the distance between average distance between stars in our galaxy. And we also know that in the universe, and this is from a simulation, galaxies are distributed, the matter is distributed. This is a distribution of matter in the universe on pretty large scales in a very non-uniform way. It's in a filamentary fashion, which we call the cosmic web. I don't know if you can hear the bird outside my window, but they are very loud in this part of Ayuka. Anyway, so we just to give you an idea of how we measure these distances, there are many ways you can actually get an idea of scales, and one is to use light as the speed of light as the basic unit, right? That's why I said think of light years, the distance that light takes to travel in a year. So, for example, light travels 1 meter in 3 nanoseconds, right? So here's a set of cartoons which I can use in a classroom. It doesn't work in Zoom, of course, but think of in a classroom that you're teaching or you're talking to people across, and the size of the room is say 10 meters or so. So it takes about 30 nanoseconds or so for light to come from one end of the room to another. And so if I'm looking at a lot of people in a normal lecture theater, as would normally happen when I would give this lecture, if somebody got out and went out of the room, the light would come to me from that person, and I would see the event 30 nanoseconds later, right? Now, my response system of my nervous system is of the order of, as you know, 1/10 of a second. So there is no perceptible lag between the thing happening and my perceiving it. So I see that event happening, or somebody comes into the room absolutely instantly, right? This is, of course, not true. And this is okay in everything that we do on the Earth. The distances are small, so that this lag of light is not that appreciable. But it is not true on the scale of the universe. So, for example, we are going around the sun, the Earth, and the sun, it takes about 8 minutes for the light to come to the Earth. So if now, think about the scenario in which the sun ceases to exist. For some reason, something happens. Not scientific, but say the sun doesn't exist anymore. What is going to happen? It will take 8 minutes for that information to reach us. Now, in those 8 minutes, no other information has come to us, not even the fact that the sun is not there. So the Earth will continue to go around the so-called sun, which is not there, because even the information of the gravitational force that is between the two objects, that information takes 8 minutes to come to us, right? So so we see the sun as it was 8 minutes ago, right? We don't know what it is, whether it is still there right now. Okay, and this distance we call 1 AU, astronomical unit, the distance between the Earth and the sun, the 8 light minutes. Okay. Now, just see that this lag has already become appreciable if you look at the sun. If you go to the nearest star, which is, say, about a parsec away, it's actually slightly more than a parsec, the nearest star, then you're actually seeing it as it was. If say it is a parsec away, so 3.25 quarter light years, so you're seeing it as it was 3.25 years ago, right? You're going around the sun's a parsec away from the nearest star. Actually, it's about 4 light years away. And so you're seeing it already, the light that you're seeing now left that star 4 years ago. Soon, this becomes much bigger. So, for example, our nearest galaxy, the Magellanic Clouds, is 50 kiloparsecs away, which is 150,000 light years. And so you're seeing the Magellanic Clouds, which is actually a satellite galaxy of the Milky Way, and I'll define all this a little later. This is the nearest little galaxy, and you're seeing that from a time, so the light that is coming to me now left that galaxy when humans were not humans yet, and that is why this cartoon shows them as cave people. So 150,000 years ago, humans weren't Homo sapiens yet, right? So even the nearest small galaxy, you're seeing it from a time that was from before the human race started. So this already tells you that we're dealing with time scales and distance scales that are much, much bigger than us, much, much bigger than our existence on the Earth. And if you look at the nearest cluster of galaxies, which is the Virgo cluster, which is roughly about 18, 19 megaparsecs, or maybe 17 megaparsecs away, it just means that it's 65 million light years away. And that means that the light that I'm looking at, when I look at the Virgo cluster, remember the central galaxy of the Virgo cluster has the famous black hole whose image was imaged by the Event Horizon Telescope. You saw on the front page of all newspapers and things like that. That particular galaxy in 87 is 65 million light years away. So you're seeing it with light that left that galaxy when the dinosaurs were getting extinct on the Earth 65 million years ago. Right. So, and that's just the nearest cluster of galaxies. And the universe is so much more big, much bigger, right? So this also tells us that astronomy gives us a very natural time machine. It gives us a way of looking at the universe in its past. We can study the evolution of the universe, evolution of stars, evolution of galaxies. And if we want to know the past, all that we have to do is to go further away. Look at things further away. We build big telescopes and look things that are very far away. Right. I'd rather not take questions right now. I will stop and I'll and see if I can take questions, because there are quite a lot of people here. So we're just going very far away, and because if you look very far away, a galaxy very far away, the light that comes to you is from that time. And this is why we are looking at a past of the universe. So we can study evolution, right? it's very similar to the fact that if you want to study how a tree grows, you don't have to stand in front of the tree for 100 years, right? You go to a forest and you look at trees at different states of evolution of the same tree, and then you try to figure out how that tree has grown. We look at galaxies or stars at different states of evolution. For galaxies, we look at going to cosmological distances, and then we can figure out how things evolve. And you will see a lot of people talking about the evolution of stars, planets, galaxies, etc. And this is exactly how they would do it. Okay. So I just wanted to show this little movie clip, which is a modern version of a classic movie called Powers of 10, which you might have seen. It's from the 1970s, 1980s, when Philip Morrison and the Eames family couple brought together a film where what you do is you look at a picture of the Earth on the human scale, and then expand that picture in powers of 10 and zoom out, and each picture goes to another picture which is power 10 times bigger, and then 10 times bigger, etc., etc. And then that kind of shows how many powers of 10 you need to go out to reach the biggest scales in the universe. Okay, so that was done with analog photographs in the 1970s, 1980s. Here's a version that Google has made, which is based on Google Earth and Google Sky and real photographs. And I'm just going to play this little clip, which is 2 minutes. The soundtrack is not important, and so don't worry about the soundtrack. But I will talk over it. But you will see what happens is that it starts from Google headquarters in Seattle, and there's some person who's there, and you go out into the universe, and you just look at the number at the bottom of the picture, which tells you the scale of the picture, and then you will see how you get a feel of how you are zooming out into the universe and the various scales that are involved. Okay, so here it is. Start with this person who is a meter across, and you're coming out of Google headquarters. Now that those arrows are 10 meters, 100 meters, looking at a little bit of the city of Seattle, and then you see the Washington State, 10 kilometers. You come out of Seattle. The picture shows now most of the western US. Now look at the bottom. You see 10,000 kilometers. Now you see Earth, 10,000 kilometers. You see the orbit of the moon, and then you come out, a lot of emptiness. Then you start seeing your planet, the sun, a lot of the black orbit, and now gone to billions of kilometers, more planets, the road cloud from the comet sun, and here you are right here, and you start seeing the nearest stars above the light. Right? And then you can see the local distance of the cloud, stars, the local galaxy. You've now gone through 1,000 light years, 10,000 light years, you start seeing the galaxy, and the galaxy is about 10,000 light neighborhood. The Andromeda galaxy, then you see the cosmic web, as I showed you, about 1 billion light years across. And then you go very far away, and it's like uniform. And then you're zooming back in, right? This is now sped up, but you can see how many powers of 10 that go to the whole universe. And then you come in, a lot of energy, and you come back to the same lady who's been lying there in the Google headquarters, and you can go then inside her eye, and you can go the other way, and then look at how the cells, and you go in powers of 10 to the blood cells. I'm going to pause there, but it's actually given you an idea of how we can go through the universe. So I'm going to pause here, and there were a couple of hands up. So let me see if I can take 1 or 2 questions. If anybody has a question, please put their hand up. and I'll try and unmute you. Yes, Amrita, go ahead. Amrita, you can ask your question. I can't hear you.
Am I audible?
Yes, please go ahead. Yes.
Okay. What would happen if there was no black hole in the center of the galaxy?
Okay, that's not a question. I mean, please ask questions on what I've talked about, right? This is something that you will hear about when we talk about black holes. This is so. Please ask if you have a hand up. Please ask a question which about what I've talked about now, because you will have lectures on black holes, and they will tell you exactly what you want to know. Anybody has a question on? So on my thing, I have Ketan who's on top. Can somebody ask me a question? Ketan, I'm unmuting you. Ask me a question if it's a question on what I've talked about now.
Good morning, sir.
Yes.
Sir, my question is, how can we determine the direction or source of light as it can go gravitational lensing?
Have I talked about gravitational lensing? No. Okay. So I'm going to switch off the questions now. I'm sorry, but there are 700 people here, and if they all ask me random questions from various fields of astrophysics, then I cannot give my lecture. So I'm going to stop this, and I'll move on with my lecture. Gravitational lensing there will be a lecture on gravitational lensing, and when that happens, ask them. Okay. Right. So let me go on with my lecture now. Okay, and I've been talking about, as I said, I was talking about the scale of the universe, and right now what I'm going to do is I'll talk about how you can see the sky. And say if you didn't have a telescope, like people didn't have telescopes, 300 years ago, but they studied the sky. So what you do is you see the sky is full of these luminous objects that we call stars. And there's a whole variation of color. Stars, some stars are blue, some stars are red, and then. But what do they tell you? Now these stars twinkle. Why do they twinkle? And this will be very important later on when we look at how we can observe the sky. You have the star giving out light, and it's coming to you, okay, in along a certain direction, but your telescope or you are on the surface of the earth, and the light comes through several layers of the atmosphere. And these the different layers of the atmosphere, because they have different temperature, pressure, density, the refractive index at every point on this path of light is different. And so this light ray goes through a very zigzag path coming to you because they're refracted. But then this refractive index is changing with time in every layer, right? And so if you look at one point image of that star that is maybe coming onto your eye or your telescope or your camera, that will move around. Like here on the right, you can see that will move around. And if you're taking a picture, you normally take a picture for a very finite period of time, then you will see that the image is blurred. And so it is blurred out to a certain distance, and that's called seen. So a star in the sky would normally have a very, very tiny angular size. But when you see it on the earth, you will see that it moves around. And they twinkle because our eyes have a response time of 1/10 of a second. And so you can actually see the image of the star moving around. Now, if it's a large object, then you don't see that moving around because the object itself is not a point object, but a fuzzy object. And so, for example, if you have a planet or a galaxy, then you don't see this effect. And that's why planets don't twinkle, but stars twinkle. But it also leads to the fact that the resolution of an optical image that you can make, if you take it with a camera and a telescope, or a camera without a telescope, it's going to be much larger than its actual size. And this is known as seeing. And one of the things that astronomers will have to do is to beat this seeing. Yeah, and we'll talk about that later on. So now what we do is when we look at the sky, as I said, I'm going to talk about now naked eye astronomy. And so what the ancients have done is they've actually drawn patterns. Humans are very good at joining dots and making shapes out of random things in the sky. But remember, when you're looking at sky like this, these stars are at different distances from you, right? You're seeing them all on the sky in 2 dimensions, but they're at different distances from you. So if you're joining them like this and calling them constellations, Bootes or Minor, whatever, they are just a point joining exercise. In real life, in 3 dimensions, these stars might not be connected to each other at all. In fact, in this particular constellation, this star and that star and that star and that star are all many, many light years away from each other, because they are, one is in the background, one is in the foreground and stuff like that. You have to remember that, okay? And the constellations that people define in the sky are done mostly to remember where you're looking up in the sky, and associations and things like that. This is very famous, the Saptarshi, which is essentially the stars in the form of a question mark or a dipper. But those stars are all at different distances from you. They are not associated with each other. Okay. Now we remember these because they make us remember the sky. And of course, one of the things that I'm going to now do is to make sure when you go out and look at the night sky, you know where you are. And this is why astronomy was important in the old times, because people used to navigate. People used to by the stars. People knew where north, south, east, west was. And if you want to go to another village, even walking, certainly when you're traveling long distances on ships and things like that, you would go by the stars. So we know in the northern hemisphere, for example, there's the North Star, which is Polaris, which is it's exactly north up there in the sky, and I'll show you exactly how to figure out where it is. And that is important, right? So, and then because we don't know the distances to these stars, astronomers use angles to measure things on the sky, okay? So you would see in the next month a lot of people talking about something is something away from something else, but they will use angles to say that. So they will not use parsecs or kilometers. They will say something's size is a few arc seconds or arc minutes or degrees. The moon is half a degree, right? Remember that. So the angular size you have to get used to, right? You know that the vertical and horizontal is 90 degrees. The moon is half a degree. The sun is also half a degree across the sky. They happen to have the same angular size. And that's why you can have a total solar eclipse. The moon can cover the sun. If you want a basic way of actually measuring things, you stretch out your hand to the extreme, and the thickness of a finger is about a degree, and your finger is about 3, 4, and 6 degrees, this finger, right? So you can actually make approximate measurements even without having angle measuring devices, right? Now, I'm trying to see if you can orient yourself with the sky. Okay, so here you are on the Earth, standing on the Earth. And wherever you are on the Earth, you can define a system of coordinates based on you. Okay, so here you are standing on the Earth, looking up. Right up is the zenith, and perpendicular to it is what we call the horizon. So this is the horizon plane, and you're on the zenith, right? Now, you're standing on somewhere on the Earth, but the Earth has its axis, its equator and pole, and you're not standing on the pole, right? You're standing here, and so the Earth's equator is like this, say, and perpendicular to it is an axis along which the Earth is turning, and that's the polar axis. Okay, so that points to, in the northern hemisphere, the north celestial pole, and in the southern hemisphere, the southern celestial pole, right? And perpendicular to that is this line called the equator on the Earth. And if you take that plane that this equator around the Earth defines, and take that plane and stretch it to infinity, you can see that it will be a plane, right? Now you can imagine, and this is what we call the celestial sphere. There is no such sphere. You can imagine there's a transparent sphere around the Earth, which is at a very large distance, just like this, because then it will allow you to think in terms of circles rather than planes. So this celestial equator cuts this plane, cuts this circle, the celestial sphere in a circle. And we call it the equatorial circle, the celestial equator on the sky. Okay, I hope that's okay. And then the axis of the Earth, around which the Earth is turning, cuts. You can see that it will go through this in the North Pole and the South Pole like that. Okay, and your zenith is at an angle to that, unless you're standing on the pole, of course, right? So how do you see the Earth? How do you see the sky? This will tell you that you see the sky and the stars in the sky in a different way from different places on the Earth, right? Because the sky is there. It's just full of stars. And you are looking at it from different points of view. Okay, so here you are. So you have the zenith and you have the horizon, which is the plane perpendicular to the zenith. But for the Earth, you have the north celestial pole, which points out, and then the equatorial plane, which cuts the celestial sphere in the celestial equator. And these two are not aligned with each other. Okay, so unless you are standing at the pole. I hope you understand this. Now, you also know that the sun rises in the east and sets in the west. Actually, it doesn't. It rises in the east exactly. So this is the path of the sun. If you are standing anywhere on the Earth, it rises exactly 21st of March or the September 21st, which is the vernal and the autumnal equinox in east, and sets in the west. Right? On any other day, it rises and sets not exactly at east and west. So what happens is that going from March into summer, like we are going now, it rises at a different point. Like here, I hope you can see my pointer. And then on June the 21st, the summer solstice, it will be farthest away from the vernal equinox in the place where it starts to rise. It will also set at a point that's farthest away from the day of the vernal equinox. So, and you can see it also spends the most time in the sky, the sun. Now, actually, the Earth is turning around the sun, but this is looking from the Earth to the sun, and you can see that. And that's one of the reasons why in summer days are longer, and the sun spends more time on above the horizon. Similarly, in the winter days are shorter, and you can see after June 21st, the place where the sun rises turns around and moves past, goes into the autumn equinox, and then moves past into winter, and days get shorter and shorter and shorter. And you can see that on the December 21st, which is the winter solstice, it's the shortest day of the year, and the sun will be above the horizon. Now, this all depends how long it will be above the horizon. It depends on the latitude where you are. Okay, the dates don't change. But, for example, if you are on the tropic, like you are in say, Jaipur or, in Ahmedabad or Calcutta, you're essentially on the tropic. Then you can see the sun go right on top of you, on the zenith, on the in the summer and things like that. And then there are, if you are in a very high latitude like Northern Europe or Canada, this sun will actually not go very far high up in the winter at all. It will be barely above and so they have long winters, and the winter days are very short, right? Now, this is what's happening really. This is a view from the Earth, but what happens is that you have the Earth, and I told you that this celestial equator, I showed you here, that's the sun's orbit around the Earth. Okay, that's the sun's orbit around the Earth, and the sun is going around in another orbit, and you have the celestial equator, and they intersect in two places, and those are the two equinoxes, and this is exactly when the sun rises the east. Okay, so that defines actually a place in the sky, because that's when the sun will be on midday on the 21st of March every year, and that's the vernal equinox. Okay, and that's where it cuts the celestial equator. Okay, and then it will do it again in the autumnal equinox. Okay. And you can see at the solstices they are furthest away from that. So the path of the sun in the sky, and it so happens that the sun is not going around the earth is going around the sun, and all the planets are also going around the sun, and they're all in a plane except Pluto, which is no longer a planet. And so you will find that if you see the sun going around like this in the sky, then all the planets will also follow that same route because they're all in a plane. And this is called the ecliptic. The ecliptic is the path in the sky which the sun takes, and also all the other planets and the moon, because they're all in this plane. Okay? So, and this is one of the reasons why in our tradition, in the Hindu tradition, as well as in the tradition of the Middle East, the Islamic tradition, as well as in the European tradition, they're all related because they all talked to each other 2,000 years ago. The Greek tradition and Islamic and Hindu traditions, all of them thought that this was a very special path in the sky, and then they broke them up into 12 different places. They called them the signs of the zodiac and things like that. Now, the sky actually moves because the earth is moving. A lot of people don't realize that actually the stars move during the night. Particularly if you live in urban areas and you've never looked at the sky, you should figure out that the sky moves. And how does it move? It moves like this, and this is a very, very, very famous picture. Now a lot of variants of this picture come, but the picture was taken by David Malin, this one, actually using a normal camera. And what happens is that this is taken from Australia. This is the Anglo-Australian Observatory. This is the main 4-meter telescope. And what he did was he set up his camera on a stand looking towards the telescope, right? Now, remember, this is in Australia, so it's a southern hemisphere. And you can see this is a picture taken with the camera open all night. And it's looking at the sky. So each of these trails is a star all night. And you can see how long it has been. It's almost 10 hours or so, because the same star has gone almost 180 degrees, about 160 degrees or so. So this is a long night. And it's kept the camera open all night. So each trail is a star. And you can then see how the sky turns. And that's because, of course, the earth is turning. Now, how does the sky turn? The sky turns around the axis, the celestial pole. And in this case, this is the southern celestial pole. If this picture were taken in the northern hemisphere, then you would see that there is a star at the center there, which is called the pole star Polaris, which is exactly in the direction of the northern celestial pole. In the south, there is nothing there. But you can see, and you can also see other things have happened. Some car came. There's an astronomer on this gangway here who's actually smoking a cigarette and is walking around, and you can see all that happened during the night. This is a picture of the whole night. But the picture that it gives us is that the stars move around the pole, and so you can locate the pole very easily by looking at how the stars are moving. And I said that I'm going to go on for another 10 minutes or so because I started very late. I hope that's okay for everybody. So, where is this pole? Now, if, for example, you were kidnapped and taken in the middle of a desert, and then you had to figure out where you are on the sky, on the earth, you can figure out your latitude on the earth very easily. Because it turns out that the angle between the horizon and how far up the pole star is, or the pole is, which defines that the stars are going around, that angle is the latitude of the place. And how is that? And you can see this here. It is if you're looking at, it's a very simple geometrical exercise that you can do. I'll quickly take you through it. Here is the Earth. and here is that's you, the observer, O, right? And say you are at a latitude, in Pune here, I'm at a latitude of 18 degrees. So this angle from the equator will be 18 degrees. That's lambda, that's the latitude. And if I'm standing here on the earth, my head is going to point towards there, right? So this will be my horizon. So that's my zenith, that's my horizon. And now I'm looking at the pole star. This is the direction of the pole star because this is how the earth is turning, right? So that's the direction of the pole star. So I've taken the direction to the pole star and I've parallel shifted it so that it's at my position. And you can do a simple geometrical exercise that will tell you that that angle, lambda, so this is 90 minus lambda, and so this angle will be 90 minus lambda, and so this angle will be lambda. And what is this angle? This angle is the distance, the angle between the horizon and the direction to the pole star. So here you can see in this particular picture, the elevation of the pole star above the horizon is about 30 degrees, and that's exactly where this telescope is in New South Wales, northern New South Wales, at a latitude of minus 30 degrees. Okay, so this tells you your latitude, right? So now I'd like you to imagine what this picture will look like if you stood at the equator. I don't know, there are 700 people here. Can somebody tell me what this picture will look like from the equator? I'll unmute Yuvraj.
Am I audible?
Yes, quick.
So it will be a semicircular kind of thing where half of it will be cut.
So why is that?
Because the south pole will be then coinciding with the horizon.
Good. And can somebody tell me what will happen if I'm standing on the pole, say at the North Pole? Can you tell me? Yashvinder? Yes? No? I can see Ananya's hand up. I am trying to unmute you. No. Okay. So with so many people, this doesn't really work. Ananya, can you tell me? Your hand is up. No. Okay. So I'll just.
So I think the circle the pole goes right on top, right overhead.
The pole will be exactly and at the zenith, and so
zenith.
All the trails will look like what?
Like complete circles.
Complete circle. So here you are. I can show you the pictures, and this is interesting because, for example, so this is where you saw where it is from anywhere else in the Earth. Here is a picture taken from the South Pole, from exactly the South Pole in Antarctica, and where there is the station, Antarctic Station of the US. And here is the same thing done with a digital camera now, but open all night. And you can see all night. And of course, in the South Pole, the sun doesn't rise. And so you can see all 24 hours. And during the winter, that is. And then you can see the stars go around. And this is exactly the same picture that Dave Malin took with the camera, now done digitally from Antarctica. And here it is on the equator. As you said, this is from Ecuador, and you can see that all the star trails in the night are semicircular. And if you look at the place where the star trails come from the horizon, they are perpendicular to the horizon. So these are essentially semicircles. So this is how you can see the sky, and you can identify exactly. And here also, because it's the southern hemisphere, there is no star in the center. But once you look at from the northern hemisphere, you can see there is a star in the center here, which does not move, and that's the pole star. That's Polaris, right? And this is a very short exposure, as you can see. This is a few minutes, and each star has moved like this. Okay. In short, the visible sky from any place on the earth. So you have to, one of the things that you should go away with if you haven't thought about this is that looking at the sky also tells you how you are oriented with respect to the earth, right? So, for example, if you are in the southern hemisphere, you are pointing downwards, right? And this is why you see the sky from a different angle. When I first went to the southern hemisphere, I looked up at the sky and I saw Kalpurush, Orion, with its head down, and it's very unnerving. And then I realized it's my head that is down, right? Because you are standing here on the earth, and your head is pointing down, right? And so a couple of years ago, I was up at the South African Observatory near Cape Town, and I was looking at the sky, and somebody said, "Look, that's the Christmas tree constellation." And I thought I'd never heard of the Christmas tree constellation, and that looked like this. But then I thought, I'm used to it, calling it Taurus. Taurus is a V. From the northern hemisphere, you see it a V. From the southern hemisphere, you see it like that, because you are pointing down. And so next time you see say Virat Kohli, finishing a century in Australia and pointing up to the sky to thank heavens or whatever, and doing the same thing in India, they're not pointing at the same thing, right? So if you are standing here and you're pointing up, you're pointing to somebody who's not in this direction pointing up. So the sky tells you exactly where you are on the earth. And here, this is a very important diagram for you to understand that if you are looking at the sky, these stars here are always in the sky because they go like that, right? These are called circumpolar stars. So all through the night, they are there, right? Now, there are stars that will rise and set, unless you're at the pole, where everything is a circle and nothing rises, nothing sets. At the equator, all stars rise and set. There is no circumpolar star. But if you are at any other place on the earth, then some stars rise and some stars set. But there will be some circumpolar stars. And then, if you are here anywhere in the universe, in this particular case, then you can see that these stars will never ever be seen all through the year, all through the night, because they will be below your horizon. And this is why astronomers have to travel quite a bit, and which is a perk of our job to some extent, but often annoying because you have to travel. In order to see a star or study a star, you have to pick a telescope that is in the right place on the earth so that you can see it, right? And it turns out that the center of our galaxy is best seen from the southern hemisphere. The most of the plane of the galaxy is best seen from the southern hemisphere. And that's why some of the best telescopes in the world are in the southern hemisphere. Okay, so I'm going to stop here now, and I'll spend a few minutes to see whether people have questions. But please ask me questions that are relevant to what I've talked about today, not generic questions about all of astrophysics, because you will find that in the month, you will have people give you lectures on various topics. Okay, so Shaunchari's hand has been up for a long time. I'm unmuting her. Please ask your question.
Yes, sir. Am I audible?
Yes, you are. Go ahead.
Sir, for one moment of time, you said that light coming from a galaxy. So, what I don't understand in general that when people say that light is coming from one galaxy has a lot of stars, planets in them. So, what does it mean by the thing that light is coming from one galaxy?
Okay, so this is something I will take up in the next lecture when I talk about galaxies. But it's a very good question, Shaunchari, and the idea is that when I look at a picture of a galaxy, I might have pictures here. When I look at a picture of a galaxy, what I would do, say that's that one. Okay, here's a picture of a galaxy, and here's a galaxy. Here's a galaxy. Here's a galaxy. Here's a galaxy. So I'm actually looking at the collective light coming from maybe the 10 to the power 11 stars in that galaxy. And each star has a different temperature, a different color, etc. But what we do is we see the collective light. Now, if the galaxy is small enough, like say that one or that one and that one, I cannot resolve it and find individual stars. In some nearby galaxies, I can actually resolve and look at individual stars. But otherwise, I look at a part of that galaxy and I see the combined light from all the stars in there, right? That's what's happening here. So you can see, does that make sense?
Yes,
You can't
yes.
actually look at individual stars in the galaxy. We now have telescopes that are capable of looking at individual stars in some nearby galaxies. It's a question of resolution. And this is why I brought up that idea of stars twinkling. Because if you're taking a picture and you're taking a long picture, then you blur out the image. And this is why individual stars are difficult to see, because they are blurred and those images blend with those of nearby stars. And this is why, because our normal resolution below the atmosphere is about a second of arc, if you know what I mean. 3,600 seconds of arc seconds make up a degree. And it's about a second of arc. The best places on the Earth have a resolution, an intrinsic resolution below the atmosphere of about maybe 1/5 or 1/4 of a second of arc.
Can you
And
sir
that is
repeat
not
once
enough.
what you just said?
Sorry. So
Okay.
the best resolution of an image that you can take with a telescope on the Earth is about 1/4 or 1/5 of an arc second. Whereas the image of a star has an angular size of 10 to the power -4 or 10 to the power -5 seconds of arc. So what you're doing is you're blurring out images of stars, and then they blend with other stars. And that's why you can't see individual stars in external galaxies far away. You can possibly do that from space telescopes, which are above the Earth's atmosphere, and that is why the Hubble Space Telescope, with which this picture is taken, for example, is very good. But there, the resolution is determined by the camera, the resolution of the camera, the pixel size of the camera. And so normally you cannot resolve individual stars in external galaxies. You see collective, and then you work with all the light and try to model what that galaxy is made of. Okay, so that's, I think, I hope that's all right. In my sequence here, I can answer 2 or 3 more questions, and I'll see Anushka after that. Anushka, I've unmuted you.
Yes, hello, sir.
Yes, go ahead.
I have a question on one of the earlier slides that you showed, the one where there was a picture of a galaxy and the distance was shown to be as 45 light years. That slide. So the idea that was presented was
there is no galaxy that is 45 light years away.
we were talking about
light years is just the nearby
the
star.
time that the light takes to travel. That slide.
Oh yeah, this one.
Next. Yes, this one.
Yeah. But here we're talking about millions of light years, right? This is.
Yes, my mistake. I'm sorry.
Yeah.
So my question is, here we consider an object which is very far away, and the light it takes the time, and so in terms of that we measure the distance, and the same principle we use to identify the objects which were there millions of years ago, and then from Earth we capture that light, but again if we see back, they won't be there because I mean they were gone, but we received the light after many years. So just like that, if there is an incident, say for example any object or any incident, like for example consider as Big Bang, so the light which was emitted at the time and the light which we received on the Earth after many years, billions of years, so what about the light which has already passed the Earth? I mean, we can't observe it
Okay,
now.
so let me just break up your question in a little way. First of all, that is what we have to live with. I said that is how astronomers work. I mean, this is all we can do. We can only study an object as the light comes to us. Okay? And we have to acknowledge that now it turns out that most things in the universe are permanent in the sense that they are very long lasting compared to our lifetimes. And so if you see a star at a distance, you assume that the star is still there, but it might have gone supernova. And then if it's, say, 1,000 light years away, we will know that the star is not there 1,000 years later, right?
Yes.
So that's all we can do. We can't actually travel faster than the speed of light and try to see what it is now, right? That's it. That's the limitation of the subject. That's the limitation of our knowledge.
But does that not mean that we are losing some significant data or the information? Because
all the data we have. We have very little data about the universe. And it's amazing how much we understand about the universe from that incomplete data. But that's all we have.
okay.
So you're looking further away and all. So from the Big Bang, the energy was created. We can't see the Big Bang, right?
Yes, that's exactly what
and then the energy that was created, we see as the cosmic microwave background. You will see that later.
Yes.
And stuff like that. And so we can only see so far away, and we have only that information, and that's it. So, but we know how far away it is from, and I'm going to spend most of my lecture this week talking about how we measure distances to things, and we'll see that there are very different ways we measure distances to things, to stars, to galaxies, and things like that. And there are many ways we can measure distances to the same thing in two, three different ways. And so we know how far away they are. And we know how long the light is taking to come to us. And we know what they look like. And that's all. That's it. That's all we know. And then we have to find the story of the universe from all this. Okay. So, okay, I can take I have so many hands up. There is no way I can do justice to this. I might need some other way of interacting with you. I will ask the organizers to maybe have some forum in which people can ask questions, but it's not humanly possible for me to answer so many questions. I'll go down and take a couple more. Jaswinder, I'm trying to unmute you. Jaswinder, see if you can unmute and ask a question. I can't see you anymore. Okay, let's go to Himanshu next. Himanshu, I've unmuted you.
Yes, sir.
Yes.
So my question is that if we look at from the galactic frame, so the Earth is executing a very complex set of motion, right? So my question is that maybe at some very large time scale, is the North Star going to shift away from our North?
Yes, absolutely. So I didn't say this, yes, but North Star is only the North Star now. It's not. It's a complicated motion in the sense that the Earth is moving, but the Earth's axis is precessing. It's like a top. The Earth's axis also has a circular motion, and that lasts about 26,000 years. This precession motion. And so, over 26,000 years, our axis turns. So, say 2,000-3,000 years ago, maybe when the pyramids were built 5,000 years ago, the pole star was Vega, Abhijit, which is nowhere near the Polaris now. It's shifted away. 5,000 years ago, the pole star was a different star, and 1,000, 2,000 years from now, a different star will become the pole star. So yes, that happens. And that is also one of the reasons why the constellations are all shifted. If you actually, somebody who follows astrology, I don't. But astrology, I don't believe in astrology. But if you look at your birth date, and people will tell you that you're Cancer or Leo or whatever, actually you aren't, because all those constellations have shifted. And the kind of things that you open up in the morning newspapers and you see that if you are born in July, you are Leo or whatever, is based on a system that was formulated about 2,500 years ago. This is how we can date this, because we can see that these constellations were such that the sun was in them all those years ago. And this is because of the precession of the Earth, right? So these things, the sky not only moves around the Earth because the Earth is moving, but the sky itself moves because on a much longer time scale, because the Earth's it's not just spinning, but the spin axis is precessing. Okay, I can I hope that answers your question. I can go back to, I've lost Jaswinder. His hand was up. But I can do another question. Tanmay, I've unmuted you.
Sir, am I audible?
Yeah.
Yeah. Sir, that you have discussed the celestial sphere model for, it's actually, the problem is that it is actually geocentric. Okay.
Yeah.
So
if
we measure some of the position of some objects, celestial objects, with respect to the celestial sphere, its problem is that Earth is actually moving and precessing. Then the star or whatever the object we are actually positioning with respect to the sphere are also moving. So there will not be any distinct position. That where
you have to
the
fix
sphere
your
is
coordinates, right? You have to fix your coordinates at some point, right? And you know all the motions because you've measured them at the precession. We measured everything. So actually, it's not that complicated at all. This is a question of spherical trigonometry that has been taught for a long time as astronomy in mathematics departments. In many universities, even now in mathematics, you read a book by Smart's Astronomy, which is essentially deals with all these coordinate transformations and the different motions of the stars, etc. Because of the different. This is all now programmed into computers. All you have to do is, on a particular date, where is a star in the sky according to what coordinates, and it'll tell you, right? So these are all very well measured and well known. In doing what I did now today, having a geocentric coordinate is useful. Now you also think about how to shift coordinates. If I did all this in a heliocentric coordinate, for example, no result will change, but it would be very difficult for you to visualize how the length of the day, the seasons, and how the stars move in the sky. And this is why we did it geocentric. But of course, the universe is not geocentric. The Earth is moving around the sun, but we know the motion of the Earth around the sun, its orbit very, very accurately, and how the Earth is turning also, very, very accurately. So these transformations can be made very easily, but it's not convenient to, when I'm teaching a class, to give you a concept, to use precise coordinate transformations in order to understand these big things. It doesn't help you understand the big picture. Okay. Right. Neil, your last question today. Neil, please unmute. Yes.
So while reading about the celestial sphere, I came across a term called the first point of Aries.
Yes.
So could you elaborate on how it's useful?
That's the first point of Aries. Here I showed you the sun's orbit and the celestial equator cross at one point, and that's called the first point of Aries, where the sun is on the 21st of March. The vernal equinox is called the first point of Aries. And herein is another very interesting thing. I told you that the sky has moved quite a bit because of precession. Okay. So let me bring up, and something I'll show next time, and I think I had it here. So here you are looking from the Earth towards the sun, and you can see it against the different constellations at different times of the year, right? So on the 21st of March, you see the sun in Aquarius, and yet it's called the first point of Aries. The implication being is that's where the sun enters Aries. And that exactly tells us when this system of astrology that people use, called the first point of Aries, comes from. Because 26,000 years, the whole thing goes around once. So for each of these houses, each of these signs are 12 times across, so it's about 2,000 years. So Aries, which is here, was in this direction on the 21st of March, 2,500 years ago. And this is how we know when we got this system. And we are still stuck with it because astrologers use that, and the morning papers use that, and they'll say that, they make predictions in your life according to a system that comes from 2,500 years ago. In any case, it's all rubbish. So that's why it's called the first point of Aries, because on the 21st of March, the sun is supposed to be entering Aries, but now it enters Aquarius. This is why. So please don't use that first point of Aries anymore. I mean, if Aristotle used it, it would have been right, but not for you. Okay? Right. So I'm going to stop here now, and we'll come back tomorrow, and I hope we won't have a delay. And tomorrow we'll start from where I was. Bye for now. Thank you for being here.